So when we last left off, we were discussing Lewis structures. Now, after covering neutral Lewis structures, or Lewis structures for neutral compounds, let's look and let's consider how we would write and draw Lewis structures for charged compounds. So if you have a cationic species, a positively charged species, then you subtract electrons equal to the charge. So, for example, a common cationic species that we'll see a lot in the acid-base chapter is the hydronium ion, or H3O+. So to calculate the total number of electrons, we have 1 electron per each of our hydrogen atoms, and we have 3 hydrogen atoms. We have 6 electrons per oxygen atom, and we have 1 oxygen atom. And then because we have a +1 charge, we subtract electrons equal to the charge, which is +1. That gives us 8 electrons total. From here, now we can assign our central atom, which is oxygen, and surround our central atom with our remaining hydrogen atoms. Okay, next we form 1 bond each and subtract 2 electrons from our total. So we subtracted a total of 6 electrons, and that gives us 2 electrons remaining. Then, following our procedure, we place lone pairs on all of our atoms with incomplete octets. And as you see, we have used up all of our electrons, and we fulfilled the octet rule for our atom. Because this molecule is charged, we place our structure in brackets, and we indicate the charge in the upper right-hand corner. This plus signifies that this entire molecule has a +1 charge, which matches the overall charge for H3O+. Does this example make sense to everyone? Any questions on this example? Well, just like for cationic species, except in the inverse case, when you have an anionic species, which is a negatively charged species, you add electrons equal to the charge. So in this case, cyanide, Cn-. So for nitrogen, we have 5 electrons per nitrogen atom. We have 4 electrons per carbon atom. And since we have a -1 charge, we add 1 electron to our total. That gives us 10 electrons. We place carbon and nitrogen as our central atoms, and just like before, we form 1 bond each. We subtract 2 electrons from our total, and now we can assign lone pairs. We assign lone pairs to our most electronegative atom first, so we use up 6 electrons. We have 2 electrons remaining. Carbon is still unhappy with this arrangement, so we place our 2 electrons on carbon. Now, as our Lewis structure, we have used up all of our electrons, but nonetheless, we still have atoms with an incomplete octet. What should we do to complete the octet for carbon? What should we do to complete carbon's octet? Double bond, sure. Okay, so we form a double bond. Is carbon fully complete? Does carbon have a complete octet? No, so we form 1 more bond to generate a triple bond. Now, as we can see, carbon has a complete octet because it has 2 plus 6, so 8 electrons total, and nitrogen has a complete octet because it has 2 plus 6, or 8 electrons total. Now, keep in mind the cyanide anion is a charged species, so just like our cation, we put our structure in brackets, and we put the charge in the upper right-hand corner. Does this example make sense to everyone? Any questions on this example? Okay, so let's keep going with this. Just like before, put the structure in brackets and indicate the charge if your molecule is charged. Okay, so we've been discussing charge, so let's bring up this idea called formal charges or formal charge. So favorable Lewis structures that you would consider good Lewis structures, have atoms with small formal charge values, 0 is best, have few atoms with non-zero formal charge, and place negative formal charges on more electronegative atoms and positive formal charges on less electronegative atoms. And in general, they have no adjacent positive or negative formal charges. Now, what is formal charge? Well, formal charge, or FC for short, is equal to the group number of the atom minus the number of bonds plus the number of lone pair electrons. Not lone pairs, lone pair electrons. Okay, so let's see how this works out, and let's talk about a trick for formal charge. The total charge of our molecule is equal to the total formal charge of all atoms in our molecule. So if we look at something like ammonium, so let's start from scratch. So we have 5 electrons from nitrogen, we have 1 electron from hydrogen, and we have 4 of them. And then since we have a +1 charge, we subtract 1 electron from our total. That gives us 8 electrons. We place nitrogen in the center, and we surround it with our 4 hydrogens and form 1 bond each. We have 0 electrons remaining. Now, let's calculate the formal charge for nitrogen. Formal charge is calculated for each atom individually. So we're calculating the formal charge of this nitrogen right here in the middle. So what is the group number of nitrogen? What is the group number of nitrogen? 5, okay. And then how many bonds do we have? How many bonds does nitrogen have? Has 4 bonds, and how many lone pair electrons does nitrogen have? Do we see any lone pair electrons? We see 0, exactly right. That in turn gives us a formal charge of +1. So then we indicate this formal charge by putting a plus next to nitrogen. We can also calculate the formal charge of carbon. Oh, sorry. Formal charge of hydrogen. I'm getting a little ahead of myself here. Carbon is a later example. So let's look at the formal charge of hydrogen. Hydrogen has a group number of 1, and hydrogen has 1 bond, and that gives us a formal charge of 0. Hydrogen will overwhelmingly have a formal charge of 0. So as we can see, if we add up the formal charge of all of our atoms, so looking at the total formal charge of all of our atoms, we have +1 for nitrogen, +0 times 4 for hydrogen, and that gives us a total charge of +1. That matches our overall charge of our molecule, which is +1.
Professor, for the hydrogen example,
Yes.
FC right above it, you said 1 minus 1. You said there's 1 bond?
Yes, so you look at each hydrogen individually. So for example, if we looked at the hydrogen all the way on the right, it has a group number of 1 and it forms 1 bond. You could repeat this calculation for each of your hydrogens and you'd get the same result. Does that make sense?
Yes, thank you.
Perfect. Any other questions on this example? Okay, let's keep going. Now, just because you have a neutral molecule does not necessarily mean your molecule does not contain formal charges. So for example, in ozone, so we have 6 electrons for each oxygen atom times 3, that gives us 18 electrons. We place our 3 oxygen atoms and we form 1 bond each. So that gives us 14 electrons remaining. Then we place our lone pairs on our outer atoms first. We get 2 electrons remaining, and then we place our 2 electrons on our central oxygen atom. As we do not have a complete octet, we take one of our lone pairs and we convert it to a double bond. Now we've fulfilled the octet rule, but let's now analyze this structure. So we're all comfortable drawing Lewis structures. Let's focus on this analysis portion. So let's look at the formal charge for the oxygen on the left. So this is going to be the oxygen on the left. Okay, oxygen has a group number of 6. How many bonds does this oxygen on the left have? Has 1 bond, okay, and how many lone pair electrons does that oxygen have? Not lone pairs, but lone pair electrons. How many dots do you see around the leftmost oxygen? 6. Yep, exactly right. And that in turn gives us a formal charge of -1. So we'd write out and we put a negative formal charge on this leftmost oxygen. Let's look at our middle oxygen. Let's look at the formal charge of the oxygen in the middle. Well, we still have a group number of 6. And now how many bonds do we have? How many total bonds do we see? 3. Yep. We have 3 bonds to this central oxygen. And how many lone pair electrons do we have on this central oxygen? 2. Yep. And that gives us a formal charge of +1. Finally, let's calculate the formal charge of oxygen on the right-hand side. So formal charge is equal to our group number, which is 6, minus, and now how many bonds do we have to this rightmost oxygen? How many bonds do we have? We have 2 bonds, and how many lone pair electrons? How many dots? We see 4 lone pair electrons on the rightmost oxygen, and that gives us a formal charge of 0. As we can see, our total formal charge of all of our atoms is equal to 0, which matches our overall charge of 0. So, it seems like our formal charge assignments were correct. Any questions on this example? Any questions on this example? If not, let's keep going then. And let's do some examples where we draw the Lewis structure for the following molecules and assign formal charges to each atom. So I've demonstrated a few examples for you. I'll do the first one and you can handle the second one. So let's look at nitrate. So nitrogen contributes 5 electrons, oxygen contributes 6 electrons, and we have 3 oxygen atoms. And because we have a -1 charge, we add 1 electron to our total. That gives us a total of 24 electrons. We then place nitrogen in the center and surround it with our 3 oxygen atoms. We then form 1 bond each, and we subtract 2 electrons from our total for each of our bonds, for a total of 6 electrons subtracted. We have 18 electrons remaining. Then we place our electrons as lone pairs on our outermost, most electronegative atoms. We've used up all 18 electrons, but we still have an incomplete octet. So we take a lone pair and convert it to a double bond. Now, analyzing the formal charges, let's look at the formal charge of the oxygen on the left. We have a group number of 6. We've formed 1 bond, and we have 6 lone pair electrons. That gives us a formal charge of -1. Calculating the formal charge of the oxygen on top of our structure, which would be right here. Again, we have a group number of 6. We have 1 bond and 6 lone pair electrons. That gives us a formal charge of -1. Finally, we can calculate the formal charge of nitrogen. What is nitrogen's group number? What is nitrogen's group number? 5, okay. How many bonds do we form? 4, okay. And we have 0 lone pair electrons on nitrogen. So that gives us a formal charge of +1. Finally, the formal charge of the oxygen on the right. We've seen this before. We have a group number of 6. We have 2 bonds and 4 lone pair electrons, giving us a formal charge of 0. Our total formal charge then becomes -1 minus 1 plus 1, which is equal to -1, which matches the overall charge of this molecule known as the nitrate anion. Does this example make sense to everyone? So you want to make sure that your formal charge of all of your atoms when added together matches the total charge of your molecule.
Professor, how did you get the double bond
In what?
for nitrogen and oxygen?
Because we need to complete the octet on nitrogen. So we
Oh,
converted one of our lone pairs into a double bond.
got it. Okay.
Does that make sense?
Yes.
Perfect. Any other questions that I can address? If not, I'd like you now to tackle the following example. And what I would like you to tell me is the formal charge of sulfur and the formal charge of oxygen. You could also share your proposed formal charge calculations in the chat, or if you're comfortable using the annotate tool, which is under the black drop-down menu under the Zoom meeting options, it would also be great if one student can volunteer and draw their structure on our class whiteboard. So I'll give everyone about 4 to 5 minutes to work on this example, and then we'll come together as a group to discuss. So don't be shy to share your formal charge assignments, such as the formal charge of sulfur or oxygen, or you can share using the annotate tool your proposed Lewis structures with formal charges for the following molecule. And if you have any questions working through these examples, don't be shy to let me know. But just make sure, in order to answer this question, you will need to draw a Lewis structure.
Professor, could you refresh my memory when we have one element, one atom of each, which one we put in the middle? Like
You put the least electronegative non-hydrogen atom.
Could you repeat it one more time?
You place the least electronegative non-hydrogen atom in the center.
Okay, got it. Thank you.
Perfect, perfect. And if there are any other questions I can address, don't be shy to ask.
So for this one, does it have a charge? I would say no.
There may be a formal charge on one or more of your atoms, or there may be zero formal charge. Once you've calculated the formal charge, don't be shy to share it verbally or in the chat, and I'd be happy to provide feedback in our group discussion. Did you end up with a formal charge of 0 by chance?
Not there yet.
Okay. So once you have your structure, you can calculate the formal charge for each of our atoms. So let's keep working on this example, and we'll discuss in about another 2.5 to 3 minutes. So we have a proposed structure for thionyl chloride, otherwise known as SOCl2. The structure itself looks quite reasonable. And if anyone else would like to share their proposed structure, don't be shy to share it using the annotate tool as well. And once we have your proposed structure, focus on assigning your formal charges using our formal charge equation. The total formal charge will be 0, but the formal charge of your individual atoms may not be 0. And let's focus on that. Let's focus on assigning formal charges to each of our individual atoms. So let's try to get some proposed formal charge assignments in the chat, and then we'll discuss this example in about another 1.5 to 2 minutes. So we have some proposed formal charge assignments in the chat. Let's try to get a few more before we discuss in about 1 more minute. Okay, so now that we have our proposed formal charge assignments, let's now discuss this example. So starting from scratch, so sulfur contributes 6 electrons, oxygen contributes 6 electrons, chlorine contributes 7, and we have 2 chlorine atoms. We have 26 electrons in total. We place sulfur in the center, we surround it with an oxygen and 2 chlorines, and then we form 1 bond each. So that in turn leaves us with 20 electrons remaining. Then we assign lone pairs on each of our atoms to complete the octet. We used up 18 electrons. We have 2 electrons remaining, and our last 2 electrons go on sulfur. So this structure fulfills the octet rule, so it's a reasonable structure to propose for this class. Let's now calculate formal charges. The formal charge of oxygen, we have our group number of 6, we have 1 bond, and we have a total of 6 lone pair electrons. That in turn gives us a formal charge for oxygen of -1. Thinking about the formal charge of sulfur, we have a group number of 6, but this time we have 3 bonds and 2 lone pair electrons. That in turn gives us a formal charge of +1. Finally, just for completeness sake, we can calculate the formal charge of chlorine, which is equal to our group number of 7 minus 1 bond and 6 lone pair electrons, giving us a formal charge for chlorine of 0. As we see, our total formal charge, the formal charge of all of our atoms, adds up to the total charge of our molecule. So when we take -1 plus 1 plus 0, that gives us a total formal charge of 0. So we apply our formal charge assignments, and we've completed this Lewis structure with formal charges assigned. Does this example make sense to everyone?
Professor, I have a question on the first one where you put the 6. Where do we get that? The 6 is it
The 6 comes from
sulfur.
Yep. So both oxygen and sulfur are in the same group, and they have a group number of 6.
Okay, I was wondering about
Where
that.
the first number comes from.
Okay, got it. Thank you.
Perfect. Perfect. Any other questions on this example?
The addition sign that you put under sulfur, now is that for chlorine, all 3, chlorine, sulfur, and chlorine?
No, just the sulfur. So I can draw it a little more closely to the sulfur, and this designates that the sulfur has a +1 formal charge.
Okay.
Does that make sense?
Yeah.
Perfect. Perfect. Any other questions that I can address?
When we draw these, do we also include the charges on each individual
Yes.
atom? Okay.
That's part of your complete Lewis structure. Any other questions that I can address on this example?
Where do you get the 1 and the 3 from?
From which?
From like the first one where it's 6 minus and then the 1.
So the 1 is the number of bonds to the indicated atom. So for oxygen, there's 1 bond to oxygen, and the 6 is lone pair electrons. Does that make sense?
Yes, so then for the second ones, there's 3 because there's 3.
Yep,
Okay.
Exactly right. And
Awesome, thank you.
2 because there are 2 lone pair electrons.
I have a question.
Thank you.
Sure.
How'd you go from 26 electrons to 20 electrons?
So you count your total, then you form 1 bond each, and you subtract 2 electrons per bond formed. Since we have 3 bonds, we have 20 electrons remaining.
Okay. Yeah.
Perfect.
Thank you.
Yes, no problem at all. Any other questions I can address? If not, let's keep working on some examples. So there's a trick to drawing Lewis structures if you're good at counting the number of valence electrons. So if you think of each atom in a Lewis structure as an individual ion or atom with a number of valence electrons and charge. For example, carbon we know has 4 electrons. Nitrogen we know has 5 electrons, but nitrogen plus would have 5 electrons minus 1, which would be 4 electrons. Now you may say, why are we doing this? What's the benefit for this? Well, if you're drawing Lewis structures, atoms and ions with the same number of valence electrons can be exchanged to give a new, equally valid Lewis structure. So for example, when we drew the structure for methane, which is CH4, structure for methane looks something like this. Now, if we think about ammonium, which is NH4+, we notice that these two structures bear striking similarity to each other. That's because we've essentially drawn a structure with the same number of valence electrons. Carbon has 4 electrons, nitrogen plus has 4 electrons as well. So this is a method to quickly draw Lewis structures using and drawing from the pool of structures that you have already drawn and are already familiar with. So it's a method of building on your previous structural knowledge. We've actually seen this also in an example with ozone and sulfur dioxide. We've drawn the following structure for ozone, and we know that oxygen has 6 valence electrons. Sulfur dioxide has a strikingly similar structure to ozone, and the reason for that is because we've essentially just replaced oxygen with sulfur. So this provides you a pretty efficient and quick way of drawing Lewis structures from structures that you already know how to draw. And it stems from the fact that Lewis structures with the same number of valence electrons and atoms containing atoms with the same number of valence electrons will often look very similar to each other. So here's a table of some common numbers of valence electrons and their common isoelectronic atoms or ions. So for valence electrons, we can look at group 5A cations and oxygen 2+ cations, or any neutral atom in group 4A. You can repeat this table for a variety of neutral atoms, cations, and anions. Note, you don't have to draw structures by analogy. You can certainly go about drawing the structures from scratch and you'd get the same results. So I'm going to do the first example for this pair, and I'd like you to tackle the second example because you can either apply the method of drawing the structure from scratch, or you can try drawing the second structure via analogy. So if we think about hydrogen cyanide, we've actually seen this one before, but we'll just do a recap. We have 1 electron for hydrogen, 4 electrons for carbon, and 5 electrons for nitrogen, giving us 10 electrons total. Now that we have our total electron count, we place carbon as our central atom and surround it with our other atoms. We then form 1 bond each, and we subtract 2 electrons from our total for each bond. 2 bonds, 4 electrons total subtracted. Now we take our remaining electrons and we use them to fulfill the octet of our most electronegative atom first. So we're going to place 6 electrons surrounding nitrogen. We've used up all of our electrons, and we still have a carbon with an incomplete octet. So we're going to form 1 bond and a second bond to make a triple bond to complete carbon's octet. So this is the complete structure for hydrogen cyanide. And what I'd like you now to do is to try to draw the Lewis structure for acetylide, which is HC2-. Now you may think, isn't that a completely unrelated structure? Well, if you count your valence electrons and you think very carefully about isoelectronic atoms, you may notice a similarity between acetylide anion, and hydrogen cyanide. So let's take about 3 to 4 minutes on the following example. Let's try to draw a Lewis structure for a acetylide anion, and let's try to assign some formal charges in this structure. So we'll
Professor,
discuss.
sorry.
Yes.
For
Please.
the previous example,
Yes.
why did you put it around nitrogen first? I'm sorry, can you repeat that?
You place your lone pairs on the most electronegative outermost atoms first.
Okay, got it.
Does
Thank
that
you.
make sense?
Yes.
Perfect. Any other questions before I allow everyone to work on this group problem solving example?
For the central atom, it's the least electronegative one that's not hydrogen, right?
Yes, exactly right.
Thank you.
Perfect. So let's work on this acetylide anion example, and we'll discuss in about 3 to 4 minutes.
Is the reason that it can't be in the center because it only has, or it can only have the one pair?
Yes, exactly right. Hydrogen in general prefers to form one bond only. So
Okay.
it wouldn't make much sense to put it in the center where the central atom typically has to form more than one bond. Exactly right. So we have a proposed Lewis structure for acetylide anion. Now all we need are our formal charges assigned, and then we're good to go. So let's keep working on this example, and we'll discuss in about another 2 minutes. So let's try to focus on and get some formal charge assignments. We're almost there with this structure. We just have to make sure we have our formal charges squared away, and then we'd be all set. And we'll discuss this example in about another minute to a minute and a half. So we have the total charge of our molecule indicated, but let's try to focus on the formal charges of each of our atoms. Are there any formal charges that we need to assign to each of our atoms? And don't be shy to chime in the chat with your proposed formal charge assignments. And we'll discuss this example in about another 30 seconds to a minute. Okay, so let's discuss this example. So we can do this from scratch to start out with. So we have 1 electron for hydrogen, we have 4 electrons for carbon, and we have 2 carbon atoms. And then we have a -1 charge, so we add 1 electron to our total. That in turn gives us 10 electrons. We pick one of our carbons to be the central atom, and we surround that carbon with our remaining 2 atoms. Now, we can then form 1 bond each for a total of 4 electrons used. And for our remaining 6 electrons, we place them on our outermost atoms first. Then, just like before, we convert 2 of our lone pairs into double bonds to make a triple bond. We've used up all of our electrons, and we now have the following structure. If you're drawing the structure by analogy, you may notice that nitrogen has 5 electrons, and carbon minus has 4 electrons plus 1. It also has 5 electrons. This is going to be a bit of a precursor here to our formal charge assignments, but yes, the carbon does have a negative formal charge. So let's calculate that. So let's look at the formal charge of the carbon in our center. So our central carbon, we have 4 for our group number, and we have 4 bonds, giving us a formal charge of 0. However, the formal charge for the carbon on the right, we have a formal charge of 5 minus our number of bonds, which is 3, plus our lone pair electron. Our group number is 4 in this case for carbon, minus our number of bonds, which is 3, plus our number of lone pair electrons, which is 2. And that gives us a formal charge of -1 for the carbon on the right. If we calculate our total formal charge, we have 0 minus 1, which gives us a total formal charge of -1, which matches the total charge observed for this molecule of -1. Does this example make sense to everyone?
Professor, on the problem on the top where we put the 1 electron, 4 electron times 2, where do you get the other electron, the 1 electron at the end?
Because we have a -1 charge for anions, you add electrons equal to the charge.
Okay, got it.
Does that make sense?
Yes.
Perfect. Any other questions that I can address? So as you can see, you can draw structures from scratch, or you can use the analogy method. Both are valid. Let's keep going and let's look at the next pair of examples. I'd like you to draw Lewis structures for carbon dioxide and NO2+. So let's look at these examples and let's work on each of these examples, trying to draw valid Lewis structures with properly assigned formal charges. And then we'll discuss these 2 examples in about 5 to 6 minutes. And if there are any questions, don't be shy to ask them in the chat or verbally. And just as a confirmation and a check to make sure that everyone's comfortable with their proposed Lewis structures, you can message in the chat the proposed formal charge of carbon in carbon dioxide and the formal charge of nitrogen in the following nitrogen dioxide cation. So let's keep working on this example. And if you have any questions, don't be shy to ask them in the chat or verbally. And don't be shy to share your formal charge assignments for carbon and nitrogen once you've drawn both of these Lewis structures. So we have a proposed structure for carbon dioxide, and it certainly fulfills the octet rule, but there may be a structure that has a better distribution of bonds that gives you smaller formal charge values. So this is why formal charges are particularly important, because by calculating the formal charge, you can determine whether or not your structure is optimal and whether your structure minimizes and follows the formal charge guidelines.
Professor, I'm kind of confused. So after we get the how many electrons, and when we're drawing our I forgot what it's called. We're drawing it. How we start with the outermost.
Yes, yes. In general, you add your valence electrons to the outermost, most electronegative atoms first. And then, only then, if you have electrons remaining, do you add electrons to your central atom.
Okay.
So we have two structures proposed, one in brown, the other in purple, for carbon dioxide. If you have another structure you'd like to propose, don't be shy to share it in our class whiteboard that we're currently viewing. And one thing that I'd always like to ask everyone to consider is, what is the formal charge on each of our oxygen atoms? And is there a structure that's preferred from this pair? Is there a structure that minimizes formal charges in this pair? The structure on the top or the structure on the bottom? Or is there another structure that we haven't considered? So let's keep working on this example, and we'll discuss in about another 3 to 4 minutes. What does everyone think? Which structure is preferred? The structure on top or the structure on the bottom? Which structure has minimized formal charges? And we can also focus on trying to draw the Lewis structure for nitrogen dioxide cation and apply a similar analysis when calculating formal charges. So let's try to get a few more responses in this class discussion. Let's try to add some formal charges to each of our structures, and then we'll discuss this example, this pair of examples really, in about another 2.5 to 3 minutes.
One bond is equal to 2 electrons?
Yes. Yes. From the perspective of electron counting, each line, each bond costs 2 electrons from your total.
Thank you.
Let's try to get more feedback in the chat. What does everyone think for these two carbon dioxide structures? If we remember our rules, a preferred structure minimizes formal charges. So which structure, the one in brown on the top or the one in purple on the bottom, would you think would be preferred? This is really important. You want to make sure that your Lewis structures are the preferred optimal Lewis structure.
The one on the bottom?
Yeah, that would, and why would you say that? Could you elaborate a little bit more?
I would say probably because it's even amounts distributed on each end.
Okay, and what about the formal charges? Are they large or small? When you calculate the formal charges, do you see 0 or do you see positive and negative formal charges?
Small.
Generally, yes. You see, actually for carbon dioxide, you see small formal charges or formal charges of 0 for all of your atoms in the middle purple structure. This is a really critical and important point that carries over to our discussion of nitrogen dioxide cation. So let's clear these annotations and let's actually discuss this example because we hit on all the major points I was looking for in this discussion. So for carbon dioxide, we have 4 electrons from carbon, 6 electrons from oxygen. We have 2 oxygen atoms, so we have 16 electrons total. We put carbon in the center, we surround it with 2 oxygen atoms, we form a single bond each, and that in turn burns through 4 of our electrons, and we have 12 electrons remaining. Then we place lone pairs on our outermost oxygen atoms until the octet is fulfilled for all of our atoms, or until we run out of electrons, which we do after we place our 12 electrons in total on each of our oxygen atoms. Okay, so now carbon is clearly not happy with this, so we convert a lone pair into a double bond. Now, for those who are curious why we convert our lone pair on the left and right to form a double bond, stems from the fact that we have to consider formal charges when deciding which structure is preferred. So we have these 2 structures to play with, and let's look at the formal charges for each. So the formal charge for the oxygen in this structure on the left is 6 minus 2 for our 2 bonds plus 4 for our 4 lone pair electrons. That gives us a formal charge of 0. Looking at the formal charge of carbon, we have 4 minus our 4 bonds, which gives us a formal charge of 0. Okay, let's look at the structure on the right and the formal charge of this oxygen. So we have a group number of 6. We have 1 bond and 6 lone pairs. That gives us a formal charge of -1. Looking at the formal charge of the oxygen on the right-hand side, this one right here, we have a group number of 6. We have 3 bonds and 2 lone pair electrons, and that gives us a formal charge of +1. The structure on the left then is preferred because it has smaller formal charges. Does that make sense? Does this make sense to everyone?
Yes.
Perfect. So nitrogen dioxide, now here's where drawing structures by analogy is pretty cool, right? We know carbon has 4 electrons. Nitrogen plus also has 4 electrons to its name. We'll keep that off to the side for now. Let's just draw this structure from scratch. So nitrogen has 5 electrons, oxygen has 6 electrons, we have 2 oxygens. This structure has a +1 charge, so we subtract 1 from our total. That gives us 16 electrons. We put nitrogen in the center, surround it with 2 oxygens, and just like before, we form 1 bond each. Now with our 12 electrons, we place our 12 electrons on our outermost oxygen atoms first to fulfill the octet of each oxygen. We've burned through all of our electrons, and nitrogen still isn't quite happy with this. Following our inspiration from carbon dioxide, we're going to form a double bond on each side to minimize formal charges. Now, why does this work? Well, by analogy, you can see that we've essentially just replaced carbon with nitrogen plus. Now, where did I get that nitrogen plus from? Well, when you calculate your formal charges from scratch, you'll see that the formal charge of nitrogen is 5 minus 4, which gives us plus 1. So all is right with the world in that respect. Next, if we wanted to calculate the formal charge of our oxygen atoms, just to make sure, we have a group number of 6 minus 2 bonds and 4 lone pair electrons, and that gives us a formal charge of 0. So the following structure that we've drawn closely mirrors the structure for carbon dioxide via analogy. And this structure, just like our structure for carbon dioxide, has minimized our formal charges as much as possible. Does this example make sense to everyone? Any questions on this example?
Professor, how do you get 16 electrons?
So we have 5 electrons from nitrogen, 6 electrons from oxygen. 5 plus 6 times 2 gives us 17. We then subtract 1 from our total because we have a plus 1 charge.
Okay.
Does that make sense?
Yes, thank you.
Are there any other questions? Yes.
Oops, sorry. Outside the parentheses, that plus, is that because NO2 plus? Is that where that plus comes from?
Yes.
Okay.
The total charge of your molecule is represented outside of the brackets in the upper right-hand corner.
Okay.
Does that make sense?
Yes, thank you.
Perfect. Perfect. Any other questions I can address on this example before we move on to subsequent examples? Okay, so let's focus on some anions now. So let's try to draw the Lewis structure for the following ion, which is carbonate, CO3 2-. So let's again spend about 4 to 5 minutes on this example, and let's try to draw a valid Lewis structure for carbonate, and let's assign formal charges to each of our atoms in carbonate. And we'll discuss this example in about 4 to 5 minutes. And don't be shy to message me in the chat any questions that you have, as well as a comprehension check by messaging me the formal charge of carbon in the following structure. So we'll discuss this example in about another 4 minutes, and don't be shy to message me with questions or to ask your questions verbally. So we have a precursor for the Lewis structure for carbonate. And we have a proposed structure for carbonate. Let's focus on our formal charges. So we have our proposed structure. Let's entertain other proposed structures if anyone else wants to share their structure on the class whiteboard. But let's also focus on assigning formal charges to each of our atoms. So let's try to get some formal charge assignments, and We'll discuss this example in about another 2.5 to 3 minutes. So the formal charge assignments that I see for each atom in carbonate look great so far. Would anyone else like to propose a Lewis structure for carbonate to continue our discussion? It's always important to entertain different perspectives for each of these problems, as there may be multiple solutions to a given problem. And if there are any questions, don't be shy to message me in the chat, and we'll discuss this example in about another minute. I've been really pleased so far with the responses from the class and everyone's participation, both verbally and in the chat. So let's write out the instructor solution for this problem, and let's discuss this example. So for carbonate, carbon contributes 4 electrons to our total. Oxygen contributes 6 electrons, and we have 3 oxygen atoms. Since we have a -2 charge, we add 2 electrons to our total, and that in turn gives us 24 electrons. Carbon goes in the center, surrounded by our 3 oxygen atoms, and we form 1 bond each. Subtracting 6 electrons from our total, we have 18 electrons remaining. From these 18 electrons, we then place our lone pairs on our outermost oxygen atoms. We now have 0 electrons remaining, but unfortunately, carbon doesn't have a complete octet. So we move one of our lone pairs down to form a double bond. Now, this molecule is charged, so we clearly have some formal charges at play. So let's calculate the formal charge of the oxygen on the right to start us off. We have a group number of 6. We have 1 bond and 6 lone pair electrons. That gives us a formal charge of -1. Looking at the formal charge of the oxygen on the left, which would be this one right here, we see the same story. Group number of 6, 1 bond and 6 lone pairs, formal charge of -1. Just to make sure we aren't going crazy, the formal charge of carbon in this case is equal to group number of 4 minus 4 bonds, which gives us a formal charge of 0. Okay, that makes sense. Finally, the formal charge of our oxygen on top, we have 6 minus our 2 bonds plus 4 lone pair electrons, and that gives us a formal charge of 0. So as we can see, if we add up all of our formal charges, we have -1 minus 1 plus 0 plus 0, we end up with a total charge of -2, which matches our molecule's total charge of -2. Does this example make sense to everyone? Any questions on this example?
When you're drawing these structures, do you have to make sure that they're being drawn symmetrically, or as long as like everything goes
Not necessarily.
Okay.
I'm drawing the structures in a certain way because these molecules have a very well-defined shape. And we'll learn later on how to draw molecules with a correct three-dimensional shape, but every time I draw a molecule, I naturally try to arrange it in a way that matches its actual shape. Does that answer your question?
Yeah, it does. Thank you.
Okay, perfect. Are there any other questions that I can address on this example? Okay, so let's keep going now. So we've already seen the example for nitrate, which is NO3+. Nitrate looks something like this. We've seen this before. The reason why I'm showing you this example is because carbon has 4 electrons. Nitrogen plus also has 4 electrons. So nitrate and carbon dioxide could be considered analogous structures. Structures with the same total number of valence electrons and that contain atoms with the same number of valence electrons. So if you're clever with counting electrons and noticing analogies, you can very quickly draw Lewis structures, even for compounds that look quite new to you. Just a point if you like to use that, or if you want to use the analogy method. It's the way I like to draw Lewis structures, as it saves me time. Okay, so we've drawn a lot of Lewis structures. Now let's talk a little bit about how we can describe the shape of our molecules. So to do that, we're going to need to invoke VSEPR theory, otherwise known as valence shell electron pair repulsion theory. You do not need to know what the name of VSEPR means. What we do need to understand is what the VSEPR theory is trying to convey. Well, bonds can be thought of as electron pairs, right? When we draw a line, we're really describing in a bond a pair of shared electrons. Well, electron lone pairs and electron pairs in bonds repel each other. Electrons repel electrons. Electrons really don't want to be near each other. Like charges repel. As a result, electrons in bonds and lone pairs are arranged to minimize electron-electron repulsions. So we want to place my bonding electrons and my lone pair electrons as far away from each other as possible. Thus, the geometry of a molecule depends on the number of atoms bonded to the central atom and the number of lone pairs around the central atom. Okay, this is what we care about. This is what determines the shape or the geometry of a molecule. So again, lone pairs and bonding electrons repel each other, and these repulsive interactions need to be minimized by positioning our atoms as far apart from each other in 3D space. So let's talk a little bit about a terminology or a term that often pops up when we talk about molecular geometry and electron pair geometry. And we call this term electron groups or charge spheres. So a charge sphere is a single lone pair of electrons or a bonded atom. Notice I said bonded atom, not bond. A bonded atom is one electron group, regardless if it's a single, double, or triple bond. We can use the number of charge spheres to calculate what's known as the steric number, where the steric number is the number of bonded atoms plus lone pairs. And depending on the steric number, your molecule will have a different general shape. The steric number is used to determine what is called the electron pair geometry, which is a rough shape of our molecule. Does this make sense so far? Do these terms make sense so far? Any questions on any of these terms? So, let's talk a little bit about different electron pair geometries. These are rough shapes of our molecule. So there are three that you need to know in this class. The first is the linear electron pair geometry. This occurs when we have two charged spheres. The bond angle, which is the angle separating our two bonds to our central atom, is 180 degrees. Notice that we can have a linear geometry for beryllium dichloride and carbon dioxide. So thinking about carbon dioxide for a little bit, around carbon, we have how many bonded atoms? How many charged spheres do we have around carbon, around our central atom? How many charged spheres? How many bonded atoms and lone pairs? Not bonds, but bonded atoms. How many atoms do we have bonded to carbon? We have two charged spheres. And that is why we have a linear electron pair geometry. Does that make sense to everyone? Again, double and triple bonds are counted as one charged sphere for the purpose of geometry. Does this first geometry make sense to everyone? Does this first geometry, does everyone understand the key pieces of information? The charged spheres, bond angle. Those are the two things you need to focus on. Okay, so let's look at another. The next electron pair geometry is known as trigonal planar. The reason why it's called trigonal planar is the molecule is flat and it almost looks like a triangle to me. There are three sources of electron density or charge spheres, and the bond angle is 120 degrees. An example of a molecule with a trigonal planar geometry would be BF3. Another example that I find a little bit more relevant would be our good old friend nitrate, which is NO3-. If we pay attention to nitrate for a moment, let's focus on our central atom. So how many charged spheres do we have centered around nitrogen? How many bonded atoms do we have around nitrogen? 3. So we have a steric number or a number of charged spheres equal to 3. That's why we have a trigonal planar electron pair geometry, and that is why we have a bond angle of 120 degrees. Does that make sense to everyone? Does this idea make sense?
Can you go over the SN equals 3? Where did you get that from again?
The steric number just represents the number of bonded atoms. And how many bonded atoms do we have to nitrogen?
Oh, 3.
Exactly right. Exactly right. So to give you a sense and to help everyone visualize a little bit of what a trigonal planar geometry looks like, I like to use a molecular model kit. Remember how at the beginning of the class I recommended a model kit to help when you reach the organic section? It's really useful for helping you see the overall shapes of different molecules. So for example, a trigonal planar molecule would look something like this. Does everyone notice how it's pretty flat? Almost looks exactly like our drawing. Does this make sense to everyone? Does everyone
Yes.
see the model kit picture? I find it's often helpful to see a picture to visualize what these molecules look like. Okay, so let's keep going and let's look at our next major group. Let's look at our next major geometry. Our next major geometry is the tetrahedral electron pair geometry. It happens to look very similar to a tetrahedron or your typical four-sided dice, otherwise known as a D4. So we have 4 charge spheres, useful for memorization because there's a lot of parallels with the fact tetrahedron, 4-sided. When you have 4 charge spheres, it becomes optimal to arrange your atoms and electron pairs in 3D space. So the tetrahedral geometry has 3-dimensional character. So for example, in the case of methane, each of your hydrogen atoms, each of your bonded atoms are arranged in 3-dimensional space, and we have a bond angle of 109.5 degrees. So, tetrahedral geometries are going to become very important later on in this class, as this 3-dimensional shape can yield very interesting properties and characteristics of more complex molecules that we'll encounter in the organic chemistry section. So we can really see the stark difference if we look at a tetrahedral molecule. Does everyone notice how we start to have some 3-dimensional character and 3-dimensional shape in our molecule? For example, what side is this red, what that we'll call our oxygen, what side is this red atom on? What side of the molecule is it on? The left or the right?
Left?
This red atom is on the left. Okay, perfect, perfect. And do you notice how this purple atom is almost in the back? So tetrahedral geometries have 3-dimensional shape, and that shape is leveraged in organic chemistry to allow molecules to recognize different shapes. We'll talk more about that later. First, we just need to get used to assigning molecular shapes. Okay, so that's the tetrahedral electron pair geometry. We're now going to add a little more nuance to this. The electron pair geometry is a rough outline of our molecular shape. The electron pair geometry is the geometry of our molecule based on the number of charge spheres. The other geometry that is more specific and more nuanced and provides the most accurate description of our molecule's shape is known as the molecular geometry, which is the geometry accounting for lone pair and bonding electron repulsion. Molecular geometry depends on the electron pair geometry and the number of electron lone pairs on the central atom. Now, why do we care? Why do these lone pairs make such a huge deal? Well, electron pairs take up more space due to repulsive interactions between the lone pair electrons. So lone pairs take up space. And as a result, these electron lone pairs will repel bonding electrons much more vigorously and will repel our bonding electrons to a greater degree. That in turn pushes our bonds, pushes our bonds closer to each other, leading to a smaller distorted bond angle. So the more lone pairs we have, the smaller our bond angle will be compared to our ideal geometry. Does this make sense to everyone so far? Does this make sense to everyone? So, what we're now going to do is we're going to delve into the molecular geometries that you are responsible for. So let's start. I like to group things in an umbrella method. So you start with your electron pair geometry, and then based on the number of lone pairs, you sort your geometry into your molecular geometry. So we're going to look at variations of the tetrahedral electron pair geometry, the first of which is known as trigonal pyramidal. In the trigonal pyramidal molecular geometry, we still have 4 charged spheres, but this time we have 3 bonds and 1 lone pair. As a result of this lone pair, we have a 107.5 degree bond angle. Remember, lone pairs take up space, and that pushes our bonds closer together, leading to a smaller bond angle. Does this make sense to everyone? Does this example make sense to everyone? Perfect. The next geometry we have to consider is the bent molecular geometry. It has 2 bonds and 2 lone pairs, and as a result, for example, in water, we have 2 bonds and 2 lone pairs. We have a 105.5 degree bond angle. Note, there's going to be some variation, plus or minus 1 degree, depending on what book you're using and depending on what molecule you're looking at. There's some variation, but in general, the 105.5 degrees is your typical bent molecular geometry bond angle. Does that make sense to everyone? Okay, so that's it for tetrahedral variants. Let's look at one more variation. This is the variation of the trigonal planar geometry, and it's known, based on the creative name, as the bent trigonal planar molecular geometry. This occurs when we have 2 bonds and 1 lone pair. Well, when I say 2 bonds, I mean 2 bonded atoms. And we have a bond angle of 116 degrees. And that's it for all the molecular geometries you're responsible for. Notice how the linear geometry doesn't have any molecular geometry variants, because by definition, you can only have a geometry if you have 2 or more bonded atoms. Any questions on this example? Any questions? Does this make sense so far? Okay, so you will have to memorize this table. You will have to be familiar with this table of electron pair and molecular geometries. So it's only 6 unique geometries that you need to be familiar with, and you will use this time and time again when we get to the organic and biochemistry section. If you can't understand molecular shape, it's going to be really hard to understand how molecules interact. Again, as well, if you haven't, and if you want a tool to help visualize molecular shape, I have a link for a model kit on Canvas. You can get a model kit new with all the pieces that you'd need to last you through this class and future organic and biochem classes for about $10 to $15. And I would consider it a useful investment if you plan on taking more chemistry and biology courses. You'll see me use the model kit throughout our lectures. With that said, let's apply our examples. Rather than rote memorization, let's learn via application. Let's be familiar with these geometries via application. So methane, from scratch, I have 4 electrons for carbon, 1 electron for hydrogen, and I have 4 hydrogens. I have 8 electrons total. I put carbon in the center. I form 1 bond each. And lo and behold, I've done a great job and I've used up all my electrons and the octet rule is fulfilled. Looking at my central atom, remember, geometry is determined for each atom individually, each central atom more specifically. So looking at this carbon, we see it has 4 bonded atoms. So not just bonds, but bonded atoms. So as a result, if I look at my table, what molecular geometry corresponds to 4 bonded atoms with 0 lone pairs? What geometry do I read off from my table?
Tetrahedral?
Yep, exactly right. Tetrahedral. So it has a tetrahedral geometry. And as a result, my bond angles are 109.5 degrees. Tetrahedral molecules have 3-dimensional shape. They, quote unquote, spring out of the page. Any questions on this example? Notice how all of this analysis is built upon the fundamental skill of drawing Lewis structures. So you're going to want to make sure you have that as solid as possible. And if you need more practice, there are plenty of practice examples that are in the workbook as well. Okay, so let's look at the following example, CNO-. I'd like you to try to draw the Lewis structure for CNO-, and then I'd like you to tell me the geometry for our central atom. Let's spend about 5 minutes on this example, and we'll discuss this example momentarily. Don't be shy to ask me any questions in the chat or verbally, and I'd like to see the response in the chat for the geometry that you determine for this molecule's central atom after you've drawn the Lewis structure. And don't be shy to share your Lewis structure using the annotate tool. And remember, more than one student can annotate, and all of the annotations, if you want, are completely anonymous. So really don't be shy to share in front of the class. So we have one proposed structure drawn. It has a lot of good points to it, and it would be a perfectly reasonable structure to draw. If anyone would like to share another potential structure for this molecule, there are multiple solutions for this problem. If you'd like to share another potential structure for this molecule, I'd be happy to have multiple options for our discussion. Or if you're still working on drawing your structure, you can look and compare your structure to that of your classmate. And you can focus then on assigning the geometry of our central atom. So let's try to get some responses in the chat. And let's try to get some other proposed structures drawn. Remember, structures should have formal charges as well. So we'll keep working on this example and we'll discuss in about 3 minutes. And don't be shy to share your alternative Lewis structures. And we'll discuss this example in about another 1.5 to 2 minutes. Let's see some assigned geometries. I want to make sure everyone's comfortable with assigning geometries, as this will be a critical skill to help you understand and mentally visualize the shape of different molecules, to understand how molecules look like, or what molecules look like in 3-dimensional space. So does anyone have a proposed geometry that they'd like to share in the chat or verbally? I see some students in the chat typing linear. Let's try to get a few more proposals and then we'll discuss in about a minute. And really don't be shy to share your responses. The act of sharing a response and formulating an opinion with a set of evidence to back up that assertion is invaluable at cementing and learning the course content. So, I see a lot of students typing linear in the chat. So let's discuss now. We have almost unanimous consensus, which is pretty interesting to see. So for the following molecule, carbon has 4 electrons, nitrogen has 5 electrons, oxygen has 6 electrons, and we have a -1 charge, so we add an electron to our total. That in turn gives us 16 electrons. We put carbon in the center and surround it with nitrogen and oxygen. There's another potential structure that puts nitrogen in the center, but that doesn't follow our rules, and we'll talk a little bit about that structure one step at a time, first and foremost. So from our skeleton, we form 1 bond each. That gives us 12 electrons. We then use our 12 electrons to place lone pair electrons on each of our outermost atoms. We burn through all of our 12 electrons in record time, and to fulfill the octet on carbon, we're going to form 2 bonds using nitrogen. Now you may ask, wait a second, why did your instructor do that? Why is this structure not okay? Well, this structure is not bad. It is very, very close in priority. The reason for the structure on the left has to do with our formal charges. So in the structure on the right, we have a formal charge on nitrogen equal to 5 minus 2 plus 4, or -1. On the structure on the left, we have a formal charge on oxygen of 6 minus 1 plus 6, or -1. So, my question to all of you is, which atom is more electronegative? Oxygen or nitrogen? Which atom is more electronegative? Oxygen. Ergo, the structure on the left is preferred. You'd get a fair amount of credit for the structure on the right. It's logically sound. And importantly, in this question design, the central atom geometry is the same in both of these structures because they're what are known as resonance structures. Don't worry about that part just yet. So in terms of the geometry around carbon, we have 2 bonded atoms. So then, if we find 2 bonded atoms, let's go to our table, which we'll eventually have to memorize. If we have 2 bonded atoms and 0 lone pairs, what geometry do we have? What geometry do we have? Linear. Yep, straight as a dart, linear, 180-degree bond angles. So we have a linear molecular geometry, and that's why our bond angle is 180 degrees. If you wanted, you could also draw an alternative structure, though this breaks some of the rules that I've shown you, but these rules, as you'll eventually see in later classes, are closer to guidelines that I'd like you to stick with just while we're in this class. There are always exceptions. For example, you can draw a structure with nitrogen as your central atom, and that would look something like this. Now, is this structure necessarily wrong? No, there's no inherent issue with it. We'll talk more about these alternative structures, which are called isomers, which are other Lewis structures that we can draw from the same chemical formula. Does this
Can I ask a question?
Yes, please go ahead.
So for the way you draw the Lewis structure, the left one and the box, that's the most correct one, right?
Because it has the negative formal charge on the most electronegative atom.
Okay, got it. And then also when you're looking at that table to see what kind of
Yes.
structure they are, it says lone pair 0, lone pair on the central atom.
Yes. Everything is with respect to our central atom.
Okay, got it. Thank you.
Perfect, perfect. So let's keep going. We still have time for a few more examples. So I'd like you to try working on these next two examples. Let's spend about 6 to 7 minutes on these examples. Let's try to draw a valid Lewis structure and identify the molecular geometry for the central atoms in the following chemical formulas. And these compounds aren't typically ones that you'd handle in the laboratory, but they're representative of common molecular geometries that you see in other related molecules. Interestingly, these two molecules you probably never handle in an undergraduate laboratory because one of them smells terrible and the other one lights on fire in air. In fact, the second compound was recently in the news. If you've heard the proposed arguments for potential signs of life on Mars, quote unquote, was the detection of phosphine in the atmosphere. Pretty interesting. You may want to look at some of the news coverage on that. Anyway, so let's focus on writing out the Lewis structures for these molecules. Don't be shy to share your responses using the annotate feature, and don't be shy to propose the geometry for each of these molecules in the chat. And don't be shy to ask questions or submit your responses verbally or in the chat. So we have one proposed structure. If anyone else would like to propose another structure for this molecule, don't be shy. There's plenty of space on this whiteboard. And additionally, let's remember to focus on the meat of our discussion, which is the geometry. And we'll discuss this example in about another 5 to 6 minutes.
So it has 2 bonded atoms.
And don't be shy to share your questions and potential responses in the chat. And remember, you can always unmute to ask a question or propose your response. So we have multiple proposed responses for the structure of phosphine. So now that we have all these wonderful Lewis structures drawn, let's focus on assigning the molecular geometry. So not just the electron pair, but more specific, the molecular geometry, which accounts for lone pair repulsions. So I see a proposal for number 1 that it's tetrahedral. That's very close. That's the tetrahedral is the electron pair geometry. The molecular geometry is more specific, and that cares about the bonded atoms and the lone pairs.
Oh, yeah, I don't get it.
And if there's a question that I can address, don't be shy to unmute and ask your question verbally or in the chat, and I'd be happy to answer. So let's keep working on this example, and we'll discuss in about another 3 to 4 minutes. And really don't be shy to chime in with the proposed molecular geometry for these 2 unique molecules.
Professor, I'm a little confused on which periodic element we put in the middle. How do we know which one to put?
The middle atom is the least electronegative non-hydrogen atom. Does that make sense?
Not quite understanding this. Sorry.
So it's the least electronegative, which means the element that is closest to the bottom left on the periodic table. And the second rule is it cannot be hydrogen.
Okay.
Does that make sense?
Yes, thank you.
So let's try to get some proposals for the molecular geometry for these 2 molecules, and we'll discuss momentarily. In about another 1.5 to 2 minutes.
Professor, for the first one, I proposed the tetrahedral. So you said it needs to be more precise. So I'm looking at the chart. So I should have said bent tetrahedral.
Yes, or you just call it bent.
Got it. All right. Okay, I see what I missed. Okay, thank you.
Mm-hmm. Let's try to get a few more responses in the chat for the molecular geometry for these 2 molecules, and then we'll discuss in about another 30 seconds to a minute. Okay, so let's clear these proposed responses and let's talk through the solution. So hydrogen selenide, selenium, has 6 electrons. Hydrogen has 1 electron, and we have 2 hydrogens. That in turn gives us an 8 electron structure. So we put selenium in the center and we surround it with our 2 hydrogens. Then we form 1 bond each. We burn through 4 electrons. We have 4 remaining. We place our remaining lone pairs on selenium, and lo and behold, our structure has fulfilled the octet rule. Now, as we see on selenium, we have 2 bonded atoms, and we have 2 lone pairs. So following our table, if we have 2 bonded atoms and 2 lone pairs, we have a bent molecular geometry. Which means our bond angle would be about 105.5 degrees. Does that make sense to everyone?
Yes. Professor, was there just any specific reason why you didn't, does that not have electrons around the hydrogens?
Because our lone pairs are placed on the central atom to fulfill the octet of the central atom. Hydrogen is sharing electrons in a bond, and as a result, it has 2 electrons in total surrounding it. Does that address your question?
Yeah, kind of. I guess I'm just kind of confused on where we get the 2.
The 2 bonded atoms from, because selenium has 2 hydrogen atoms bonded to it.
Oh, yeah. Gotcha.
And then it has 2 lone pairs because of the 2 lone pairs. Does that make sense?
Yes. Thank you.
Perfect. So for phosphine, pH 3, so we have 5 electrons from phosphorus, we have 1 electron from hydrogen, and we have 3 hydrogens. That gives us 8 electrons in total. We place phosphorus in the center, we surround it with our 3 atoms, and then we form 1 bond each. We used up 6 electrons, we have 2 electrons remaining, and our 2 electrons go on our central atom of phosphorus. Now, from that information, we can assign our geometry on phosphorus. So we have 3 bonded atoms, and we have 1 lone pair. So what geometry would we expect then from 3 bonded atoms plus 1 lone pair?
Trigonal pyramidal.
Yes, exactly right. We have 3 bonded atoms, 1 lone pair. That's a trigonal pyramidal geometry. So that's trigonal pyramidal. Does this example make sense to everyone?
Professor, on the chart on the table, when it says electron groups, what number are those? Like you said,
That's the charge sphere. That's the total. And the bonded atoms and lone pairs are more specific. So in total, we would have a steric number or a total number of electron groups of 4. But in those 4 electron groups, we have 3 bonded atoms and 1 lone pair. Does that make sense?
no, I didn't get it. What are they?
The electron groups are the total number of bonded atoms and lone pairs. It's just like a charge sphere.
Okay, bonded atom and lone pairs. Okay.
Does that make sense?
Yes, thank you.
Perfect. Are there
I
any
have a
other?
question.
Yes.
What's a lone pair? I'm confused.
A lone pair is a
Yeah.
set of 2 electrons that
Oh,
are
okay.
participating in bonding. They belong
Oh,
only to the atom that they're assigned to.
okay. Thank you.
Perfect. Are there any other questions that I can address?
And Professor, for the bend, for that example, it says bend. Why
Yes.
did you say that angle is 105? On the chart, it says 109.
It's less than 109. On the table, it has the less than symbol. What that means is that the bond angle is less than 109.5. And if we go back all the way to our discussion of the bent geometry, I mentioned that the bond angle for the bent geometry was 105.5. Did that address your question?
Okay. So now in the picture, it says 104.5. So
Yes, there's a little bit of variation by about 1 degree, depending on your molecule and depending on the book.
okay.
Some
Thank
books like to say 104.5, others say 105, others say 105.5. As long as you recognize that the more lone pairs you add, the smaller your bond angle becomes, that's really what we're looking for in this.
Okay, thank you.
Perfect. Are there any other questions that I can address?
Just real quick, Professor. So for that last example that we had, are we not, we did the 5 electrons plus 1 times 3 equals 8 electrons. So we just kind of automatically assume that all the hydrogens have all the electrons there. We don't have to draw it out.
What do you mean? We complete the octet for each hydrogen by forming 1 bond. Hydrogen only needs 2 electrons for a complete shell.
Okay.
Does that make sense?
Yes, thank you.
Are there any other questions that I can address before we close out today's session? If not, I will see everyone either in office hours. I have office hours today from 12 to 3 o'clock. I have office hours also on Tuesday and Thursday, as well as the mentorship program on Tuesday and Wednesday evenings. If there aren't any other questions, we'll end today's recording.
I have a question.